Doot, 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 doot. Doot, 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 doot. All right. All right, everyone. I want to go ahead and start class. I have your quiz from last time that you turned in. I'll give those back to you maybe when we do our break. I want to talk about the final exam. A lot of people have been asking me about the final. Here's the plan on the final right now. The final will only cover things like implicit differentiation, related, I know you're going to get mad, rates, and then pretty much chapter 4 and possibly 5.1, depending on how far we go. Now, chapter 4, that's a big deal. I mean, that's everything we've been doing since the test, right? Well, yeah. You know, the max-min stuff and all that. It's curve sketching, word problems. But people want to know, is it comprehensive? How far back are we going? Well, I'm not going to test you on every little aspect of the class that we've gone through. Those are the major topics. So the only thing really from the past are these two. Now, that's kind of like option 1. Option 2 for the final is for someone who really is trying to bump their score up. Okay, so maybe you're in a situation where I told you, look, you need 100 for a B. Like, you can pass the class, but you need 100 for a B. So you're like, okay, I can't get a B. Well, I'm willing to offer more points to you if you want to take option 2 for the final. And option 2 would be comprehensive, okay? I'm just going to say it would be comprehensive. And all I'm going to tell you on that is to go study the other exams. Go study exam 1, go study exam 2, and the same things that I put on there above, right? Those same things are going to be on that comprehensive also. So it's going to be a longer test and a harder test. But it can up your score on one of your old tests. So like maybe you got a 40 on a test, you take option 2, and I'm not going to say I'll replace that score, but it will come up, all right, if you do better. It's like a bonus, yeah. Now, you have to choose, okay? The day you come in and take the final, you have to choose which one do you want. If you're happy with your grade, just take the first one, get it over with, get out of here, you're done, right? You take option 2, well, bring a sleeping bag. No. It won't take that long. But it'll be long, you know. It'll be the full, what, how long are we here? 3.5 hours or something like that? It'll probably be the full 3.5 hours. Yeah. I don't know. I haven't made it yet. Yeah. Okay. We can talk more about that later. Monday, we can talk more about the final. I'll try this weekend to put something out on the web as a review for the final. The only thing I'm going to really put a review out for is option 1. Again, option 2, I'm just going to say go study your old tests. And the solutions to exam 1 and exam 2 are now on the web. Okay, if you go to our Canvas and you click on Files and go to Solutions, they're there. And I also put on there just today, you know where all our class videos are? Some of you do, some of you, I don't know if you've ever gone there, but if you go to where I've been recording these videos, under Solutions, under the videos, I just put problems 11 and number 11 and number 22 from 4.4. That's the sketching, those curve sketching problems. Number 11 and number 22 I did. It took me like 45 minutes to do both problems on video. And then in Canvas, under Files, under Solutions, I put the PDF of everything I wrote for that video. Because I think those problems are so important, you're going to see it on the test. I wanted to give you 2 more examples that you could go back and look at. Okay? All right, the rest of what we're going to do today is finish Chapter 4. I will entertain any questions you have over homework or over anything related to this class. Anyone have anything for me? You ready to go? All right, so the curve sketching is where we ended up last time, right? I've only shown you 1 curve sketching problem. That's it, in class. You now have the other 2 I put out there for you, so now you have 3 to go off of. They're all a little bit different. I mean, there's little subtleties within each problem that make them different. You know, the way that you find the x-intercepts, the domain issues. So the only way to get good with those is to practice them. I'm going to avoid on the test giving you anything like ridiculous, because some of the problems in here get really challenging. So, you know, stick with the ones kind of in the teens, like 1 through like 28, something like that. How'd your thing go? It's good? All right. So I don't intend on covering anything else in 4.4 today. I'm ready to move on to 4.5. So for 4.5, I'd like to start with 2 basic ideas we have here. Okay, they're very different. Finding max min on a closed interval and finding local max, local min on implied domain. Let's talk about the differences between these 2. If I was on the left side here, finding the max min on a closed interval, I'd be looking at a function, right, that started at some point, ended at some point, and I'd be trying to locate the highest and the absolute lowest, right? Those 2 points would represent the max and min. What is the technique used to do that? What kind of give me, if you can think it, if you know it in your head. So you do the derivative, set it to 0, figure out where it's undefined, right? So find the critical numbers, right? What do you do with those critical numbers? Plug them into the original function. And then what else do you plug into what? Endpoints into the original function, right? So, I mean, if we're just trying to like real rough sketch of how you do this, you make sure it's continuous, right? You make sure it's on a closed interval. You find the critical numbers. Then you look at the endpoints. You take those critical numbers endpoints, plug into the function f, right? That's the basic idea. But we have to have a continuous function on a closed interval to do that. What we did in the last section, in the curve sketching and the one before it, is we said, well, what if we have a function and we don't have a closed interval? Our function is defined on whatever its domain is, and we want to go and try and find max, local max and local mins, right? The process for doing that is very different. What do we do here? I'm talking just local max and min. If I ask you to find local max, local min, not sketching it, not all that, concave up, concave down, just if I ask you to find local max and mins of this, how would you do it? Okay, so you do derivative, set to 0, figure out where it's undefined. So we'd still be finding the critical numbers, right? Right? We'd still do critical numbers. But then what? Number line, right? Then we do number line with the critical numbers. Then test points. Where do we plug those test points into? Into the derivative, right? What does that tell us? Positive means up and increasing, negative means decreasing, right? So there we're able to make that like table that shows arrows going up and down, up and down. And then what we're looking for is where it goes up, down is a max, and where it goes down, up is a min, right? So I'm just going to show under this like up, down, up, something like that. We make number line. Is that enough for you to just look at it and kind of know what I'm talking about there? We also had to be careful, right, with that. Whenever we had the switch, like it goes from up to down, what did we have to make sure about that point right there at the bottom there? What do we have to, before we could say that was a local max or something, we'd have to make sure what? Is what? That yet the function exists there, that point's in the domain, right? You cannot have a local maximum at an asymptote. So we have to be careful. So do you see though that there are two very distinct and different approaches to trying to find maxes and mins on closed intervals versus maxes and mins on an implied domain? Yes? Okay, the section we're going to do now are word problems. And every word problem we look at is going to fall into one of these two categories. It's either going to be trying to find the max and min on a closed interval or find the max and min in the entire domain. Okay? Depending on which one it is, that will dictate which method we use. All right? It's going to be in the problem somewhere. No, it's not always going to be clearly, an obvious thing. Okay? But if we notice it, then it makes the problem a lot easier. Because wouldn't you agree that the closed interval method is easier? I mean, it's just critical numbers, plug in, done, compare, next. So, all right.
Why can't you just plug in where the applied domain? You just plug those numbers into the function, but still know which ones are higher than the others.
Yes, that's true. You'll know which ones are higher, but you could have a lot of different local max and mins, right? Like, let me just show you a picture real quick. And so, like, let's say I had this. So to get this, you would have to actually compare. I mean, there would be a lot of different comparisons, right? And you have the highest one would be at the end. I did that intentionally. So I guess answering your question is that just because 2 points, one is higher than the other, if there's a lot of them, then you have to compare each one. I don't know if that...
Well, one's going to have to figure out if it's increasing or decreasing on all those.
You would have to do that also, yeah. There would be no way around it. Let me think more about this. Let me think while I'm writing out the note. That's a good question. Continuity clip. I'm going to think while I'm writing. On the notes for 4.51, we have a set of steps. Does everyone have the notes printed out? Yes, for chapter 4? I'm looking at 4.51. It's going to be 6 steps. We have once again reached a point, that's where I'm reading, where we can apply what we've learned so far to some interesting word problems, applications. Here are the basic steps for solving these word problems. Read and understand the problem. Draw pictures. Introduce notation. Determine the variable to be optimized. Find the objective function. Express the variable to be optimized in terms of the other. Use the given restrictions information to express the variable to be optimized in terms of one single other variable. Use the methods of this section to find the absolute max or min of your function. Pay attention to whether or not your function is defined on an open or closed interval. Okay? So this all doesn't make sense until we do an actual problem. So I'm going to look at this first one that I have in my notes. It says, find the maximum area of a rectangular pen if you have 100 feet fence. Now, in my video, I went through and showed you the different ways that you can have a 100-foot fence. Now, honestly, how many of you watched the video? It's okay if no one did, but so you understand that there's many different ways you can have a pen out of 100 feet of fence, right? And each one of those has different areas. So what shape gives you the maximum area? What dimensions? What do you think it is? 10 by 10, a square, right? A perfect square. That would make sense, right? That would give you the most area, 10 by 10. But is that using 25? Is that going to give you 100? It's saying 100 feet of fence. We're saying 100 feet of fence. 25 by 25. I think you were thinking I have 100 square feet of area. 25 by 25. Should give us the most area, right? Should be, but it's a question. So let's try and do this with the calculus, all right? Find the maximum area of the rectangle you want to have. So I'm going to read it. I kind of understand it. Do you understand it, what we're looking for? What are they asking for? The maximum area. So our final answer should be an area, shouldn't it? Draw a picture. Well, a general picture of a rectangle looks like this, right? It has a length and it has a width, or we call that height. It doesn't matter. That's the general picture. Now, don't mistake this with like related rates where we did a general picture in an instant in time, because we have no instant in time anymore. Time's not running in the background. It's just we need to build a rectangular pen. So I've drawn a picture. I've introduced some notation. Determine the variable to be optimized. What do they want optimized? So think about when we talk optimization, think maximum, minimum, max, min. What do we want the max or minimum of here? We want the maximum area, right? So the thing that we want to optimize is the area. Okay, we want to optimize the area. Get the most area possible. So come back down to my picture. Do you have an equation that relates that rectangle to area? Length times width. So I'm on step 4 right now. Express the variable to be optimized in terms of other variables. Right? Area is equal to length times width. Now let's look at number 5. Use the given restrictions or the given information in the problem to express the variable to be optimized. So that means to express which variable? A. So they want us to express A in terms of one single other variable. Right now, in order for me to know the area of a rectangle, I need to know the length and its width. But I'm supposed to use some information that's given to me in the problem to get it to be only in terms of L or only in terms of W. So what have I not used in this problem? I have 100 feet of fence, right? I have 100 feet of fence. Haven't used it. Well, how does that relate to my picture? If that means the entire distance around this thing has to be 100, right? That's right. So that means that 2L plus 2W equals 100? Yes? This is known as a constraint. What we are trying to come up with here is what's called the objective function, which I'll write down as soon as we get it. So it's like we can make any rectangle we want. L and W can be anything. But as soon as I tell you you have to use 100 feet of fence, I've constrained you, haven't I? I've changed what's possible for you. So that equation is my constraint in this problem. And what I'm going to do is I'm going to solve it for either L or W. So divide everything by 2 first, right? And then 50 minus W. I could have solved for W. I just chose L because I kind of looked up at the equation up there. A equals L times W. It wouldn't matter if I replaced L or W. It'd pretty much look the same. So now rewrite A up there. What would it be? What is L? 50 minus W times W, right? So area equals, I'm going to distribute that W through 50 minus W squared. Do you all agree with that? And now I'm going to add one more thing. I'm going to write A of W equals 50W minus W squared. All I did by putting A of W in there is I've stressed the fact that now A is dependent upon W. As soon as you tell me what W is, I can tell you the area. I don't need to know L. Oops, sorry. I forgot to mute that. I can't believe that man's calling me right now. I'll tell you all that story if I have time. Can't get people to do good work on anything these days. Okay, so putting the W in parentheses there just stresses that this is a function of W. That's what I'm going to write underneath it right now. This is the objective. Now, what we want to know, remember, what were we trying to optimize here? The area. We're trying to find the maximum area, and I now have a function that represents the area, don't I? It's a function of a single variable. Well, that means I should be able to find its maximum, shouldn't I? How do we find the maximum of a function? Well, it depends on if it's on a closed interval or an open interval, right? It depends. So how can we determine if it's closed or open? What's the variable in this problem? W. So the question is, can you put a restriction on W or not? Is there a maximum that W can be or a minimum that W can be? What would the smallest W could be? Sorry, that's kind of weird to say that. Imagine that you're out there and you got 100 feet of fence and you're like, all right, let's build a rectangle. Right? You know, have you ever seen like those rolls of fence, like the, you know, chain link fence or something? Let's say we have a 100-foot roll, right? Couldn't we put off our picture, right? This is LLW. We have to first determine, let's say, what's L going to be, or what's W. We could choose. Let's say W. We could say, let's let W be 50. Then you would have the whole fence, wouldn't you? You would take it and you'd cut it in half and 50 on each side, and then you'd say, shit, I don't have anything left for L, right? That's one way we could do it. But you wouldn't even have a rectangle, would you? So 50 would be the absolute biggest value you could ever use for W. What would be the smallest you could use for W? 0. And then use the rest for L, right? No one would ever do that, but the thing is, can we fix our W between two numbers? Yes. So we could say 0, and you can't say 100, you have to say 50 here. Does everyone understand why it's 50? Because W represents the two sides. If you say 100, right? If this right here was 100, then come into this equation right here, your constraint, and replace it with 100, and what would L have to be? Negative 50. But if you put a 50 in there, then L can be 0, and that's okay, right? Yes. Because we need a closed interval. Okay. Basically, we would be making a fence making a rectangular pin that had no length to it if we did that, which would be absurd, but we want to include 50 because it makes the closed interval happen. Yeah, I mean, it's physically it's kind of weird. It has no width, which lines don't have a width, right? Lines are, you know, from point to point, there is no width, just like a single point has no width to it. Okay. All right, so do we have a continuous function on a closed interval? All right, this is a continuous function. It's on a closed interval, and therefore we'll do it what we call the closed interval method to find it. So we'll need to take a derivative, right? A prime W equals 50 minus 2W, right? What are we supposed to do with that? Set it to 0, find out where it doesn't exist. If it doesn't exist, I don't have to worry about, right? Because it's actually a linear equation, or linear function at this point. And set it to 0. You get W equals 25, right? So that is a critical number. Does it live inside of our interval? Yes. Okay. So all I have to do now is evaluate the original area function there and at the endpoints, right? There and at the endpoints. So I need A of 0, A of 50, those are my endpoints, A of 25. I think those are pretty easy to plug in, right? You should get 0 if you plug in 0. You should get 0 if you plug in 50. And you should get 25 squared if you plug in 25. So it's pretty obvious what the maximum area is going to be, right? Where it's going to come from? 25. So they asked for the maximum area, right? But in a problem on a test, I might not ask you, what's the maximum area? I might ask you, what are the dimensions of the pin that give you the maximum area? So you would have to, from this, you know that what? W was 25, right? Which means that L must be, and you would go back to the equation you have for L there, plug in 25, and in this particular case, L would be 25 also. Right? Okay. Now this is about as easy as it's going to get right here. It's about the easiest problem that we'll ever do for optimization.
Do all these have constraints?
They all will have a constraint. They just won't all have closed intervals. Yep. And anyone who's taking Cal 3, who are my Cal 3 people? Okay, a few of you. This will extend into functions of, where you have functions of two variables. So where you get like three-dimensional surfaces. I mean, imagine like a sheet kind of like waving around in the wind, you know, and you say, stop. Okay, and you look at that surface, you can find the highest and lowest points on a surface using something like this. You'll have an objective function and a constraint. Objective function, constraint. Next one. So I'm going to do the next example in here. This was that beer can problem. It's a 1 liter beer can. I'm going off my notes. I tell you that I want to make a beer can that's a right cylinder, right meaning 90 degrees. So I have a right cylinder. It must hold 1 liter, which is 1,000 cubic centimeters. Find dimensions. Oops. Dimensions of the can with smallest or I should say the least surface area. Why would anyone want to answer this question? And why would it be useful?
Surface area affects shape.
Okay. Okay. So it could have something to do with energy transfer, heat transfer. Less material. Like let's say that I'm shipping out beers a can, right? There's a lot of different ways I can make a can to hold 1 liter. What I want is the one that I have to order the least amount of aluminum for, right? I mean, imagine a can that looked like a test tube, right? You know, that was maybe like 1 millimeter wide and very tall and held 1 liter. I would use a lot of aluminum to make that. Well, that's what the video was trying to get you to see, is that you can have a can hold 1 liter that has a certain surface area and then change the shape of the can, still hold 1 liter, but now you have a different surface area. Right? There's so many ways to hold 1 liter. Which shape can uses the least amount of surface? Because that's what we want to build, right? That's what we'd like. Okay. Yeah. All right, so let's try and set this up. Read and understand it. Draw pictures. I've kind of already got a picture here. If this is a can that I get to create, then it's going to have some radius and it's going to have some height, right? Yes? What is the variable we want to optimize? So I'm looking at, I'm doing step 3, introduce notation. Determine the variable to be optimized. Find the objective function. So surface area, right? You would say, I tried not to use the word minimum because I'm trying to kind of sneak it in here, but it's hard to sneak minimum in without being obvious. The smallest surface area means minimum surface area, right? So minimum or maximum in some way is going to be given to you in the problem, right? Somehow. That determines the variable we're trying to optimize. So I don't like writing SA, so I'm just going to put A to mean area. Is that okay? So I want to optimize A. So I'm trying to optimize A. Okay? So what do you need? Yeah, I mean, what's the area of a can? You need to be able to figure that out. What is the area of a can?
Cylinder volume equals pi r squared h.
Yeah, that's okay. Look at me real quick. I'll show you this.
Oh, okay, it's pi r squared h. No.
Look, everyone. Here's a can. Okay? What's the area of the top of the can? What's the area of the top of a can? It's the area of a circle, right? What's the area of a circle?
2 pi r.
Nope. Pi r squared. Pi r squared, right? That's a circle right there. So that's pi r squared on top. What's the area of the bottom? Pi r squared, right? Now, take your scissors and cut this can open. Okay? Just cut it open. What do you have? Length times width. How high is it? Well, the height of the can, isn't it? How long is it? It's the circumference of the circle, isn't it? Which is 2 pi r. So if you take that can and you cut it open, you have two circles, right? I've cut it open, taking the tops, the two circles, pi r squared here, pi r squared here. This is the height of the can, and the distance across here is the circumference of the can, which is 2 pi r. So the area, the surface area of a beer can is the area of this part, which is 2 pi r h plus pi r squared plus pi r squared, so 2 pi r squared. You don't need a formula sheet for that. I mean, it's easier to reference. But this is one of those things that I like to point out when I can, the difference between memorizing something and understanding it, right? If you can just visualize it, you can see where it comes from. So that's the formula though, right? You have your formula sheet just in case, right? 2 pi RH plus 2 pi r squared. How many variables does A depend on right now? What would I need to know in order to tell you the area of this can? The radius and the height, correct? We cannot find the maximum and minimum of a function if it has two variables in it. We need a single variable. So the only way we can get this down to just r and just h is to use what? What did we use in the last problem? Because we drew a rectangle. We say, oh, we could draw any rectangle we want. What was it that made us be able to eliminate one of the variables? The constraint. That's right, the constraint. So what's our constraint in this problem? What is it about this beer can that has to be true? It's got to have good beer in it, right? Can't be skunky beer. Well, what is it about the can that has to be right? The volume. It has to hold 1 liter. Yes, question.
When you cut it, isn't the length just the circumference length?
That's this length, but I want the area. So length times height gives you that area right there.
Why do you have to have the r if it's just the length of the circumference times the height?
Why do I need the r? 2 pi r is the circumference of a circle. See, when I took that can, 2 pi r. So you're okay with it then? Okay.
2 pi r and pi r squared is different.
Yeah. We're good? Okay. All right, so we need the objective function, right? Or not objective, we're getting there. The constraint. This can't be just any beer can. It must be a beer can that holds 1 liter. So what does that mean? The volume must be 1 liter. Now I'm going to use 1,000 cubic centimeters instead of 1 liter. I'm doing that because then my radius and height answers, whatever it is, will be in centimeters. What is the volume of a can, though? What's the volume? It's a different formula. It's pi r squared h, isn't it? Pi. Are you looking sphere or something? Okay. Pi r squared h is 1,000, right? So isn't that an equation right there, a constraint? I know that pi r squared h must be 1,000. So can you solve that equation for either r or h? Which would you like? H? Yeah, me too, because then I don't have to do a square root, right? So let me, how do I get h by itself here? Divide both sides by pi r squared. All right. Now, are you ready with that constraint to come back to the objective equation and try and plug in, replace h? So a equals 2 pi r, but then h is 1,000 over pi r squared plus 2 pi r squared. Anything good happen there? I do get a pi to cancel here and one of the r's, right? And so I have what, 2,000 over r plus 2 pi r squared. Questions? Is that now an equation that the a only depends on one variable? So I can write it as a of r equals 2,000 over r plus 2 pi r squared. That's my objective. What should I look at next? Before the derivative, be careful. This is a critical step. I mean, you'll need the derivative no matter what, but yeah, is it open? Is it an open interval or a closed interval? So what's the variable? R. Is there a restriction on R? R is the radius of the can. Is there a smallest radius it can be? Can it be 0? Look at your function for area. Not only that, look at h. If you try and plug in 0, what's your height then? You can't make a can that has a 0 radius. You cannot make a can that has a 0 radius and hold 1 liter. Can't happen. Right? Well, but let's talk about the rectangle. There was nothing on the rectangle except for the fact that the total length of the sides had to be 100, right? So when I used 50 on each side, I still had all 100 feet used. It's just the other 2 sides had 0. So my rectangle didn't form a rectangle, but I still have an area. The area was 0. So I didn't have any true violation of any mathematical operation there. Does that make more sense? Here, if you try and let r be 0, your height is undefined and you won't be able to hold the liter. Now, is there a maximum radius? Think about this beer can. I mean, I could have this ridiculous beer can, right? That one right there. It's just like a wafer. It's just like this big wafer sitting on the table. You could I keep letting that radius get bigger? And what happens to the height? Gets smaller. But you could go forever, right? I could have a radius that's 3 miles long and the height would be infinitesimally small. So it's theoretically, there is no restriction on radius. Do you see that? So what we would say here is the smallest radius would be 0, not including 0, right? Cannot be 0. And the biggest it would be, well, it would have to be less than infinity. In other words, it's an open interval. And we are not to use the closed interval method for this. So what I'd like for you to do is take this the rest of the way, and it's going to be your quiz. Okay, I'm gonna just real quick go through the rest of this. The derivative, right, because this is an open interval, you take the derivative, you should get negative 2,000 over r squared plus 4 pi r, right? And then what you need to do is set it equal to 0 and find out where it's undefined. So let me first set it equal to 0, and this is where I think some people ran into some issues. I'll show you what I normally do. Like my normal protocol on something like this is to get a common denominator. Like I wouldn't multiply both sides by r squared. I get a common denominator, and that means I have to introduce an r squared on top and bottom there. And so it creates this new negative 2,000 plus 4 pi r what? Cubed over r squared equals 0. And that's what I like to work with. Now, a fraction can only be 0 when? When the numerator is 0. So it turns out to be the same equation, but what I don't eliminate here is what makes it undefined. See, I still know what makes this undefined. 0 makes it undefined, right? If you multiply both sides by r squared, you lose that. So just FYI there. And then you bring things around here. Let's divide everything by 4. Take the 2,000 to the other side, divide by 4. Pi r cubed equals, what, 500? Divide by pi. 500 over pi is r cubed. Take the cube root. Cube root of 500 over pi. That's the only critical number I have so far, right? This right here is the work I did to figure out when the derivative was 0, right? Now, where's the derivative undefined? At r equals 0, but I don't really need to consider that because that's not even in the domain, right? That's not even in the domain of this problem, so I don't need it. But these are the things I look for when I'm grading. Are you doing these steps? Okay, next thing is what? That's the answer? Number line. See, this is another thing. Students on tests won't do this step. If it'll be wrong, I won't count it right. Because you have to show me it's a minimum or a maximum? Minimum, right? So square root or cube root of 500 over pi. And then I have to pick something on each side of that, right? But I can't go less than 0. So what is 500 over pi and then cube root? It's definitely bigger than 1, isn't it? Because I'm picking a test point. It's 5.7. So 1, I'm going to pick 1 as a test point. And then I'm going to pick something to the right of it, like, I don't know, 6, 100, doesn't matter. Just got to be to the right. And I'm going to plug those into what? The derivative. So what is the function? It's a prime. Let me do a prime of 1. And the derivative was negative 2,000 over r squared, right? Plus 4 pi r. Wasn't that the original derivative? Negative 2,000 over r squared plus 4 pi r. The question is that number positive or negative? It's negative. So that tells me the original function a the area function's going down over here. That's a really good sign, right? Now, test 100. Negative 2,000 over, what's 100 squared? And then plus 4 pi times 100. So negative 2,000 over 10,000, that's a decimal, negative little decimal, smaller than 1. And then add a pretty big number to it, 400, 507, right, like 1,200 or something. It's positive. So what can I say? I have a local minimum at r equals cube root of 500 over pi. Yeah. And then I need to get h, right? So how do you get h? We had a formula for it, didn't we? Way back in the beginning here. There it was. 1,000 over pi r squared. So it'd be something like 1,000 over pi times r, which is the cube root of 500 over pi squared. And you can just figure out what all that is as a decimal. Approximately, what did you guys get over here? Okay. Something like that. So the answer to the question would be the radius is 5.419 centimeters, right? And the height of the can would be 10.83 centimeters. And it actually turns out that if you did this problem just in general, the way to get the least surface area on a can is if you let the radius be equal to half the height. In other words, let twice the radius be equal to the height. Notice that the height is double the radius. That's not a coincidence. It'll always work like that. If you wanted a liter, or if you wanted 12 ounces, or if you wanted 6 ounces, no matter what, the least amount of area that you're going to get for a cylindrical can would be letting the height be twice the radius. Or if you want, since twice the radius is the diameter, if you let the diameter of the can be equal to the height of the can, that's going to use the least amount of area. So let's say I pick a can that's that wide. I would want to make it just as tall as it is wide. And that would use the least amount of area. Right? This, if those were the same. What's the what? The line test? We had to make sure that it was going down then up to verify that it is a minimum. Yes. It's verification. We have a pretty good idea. It's the only critical number we have. We have a pretty darn good idea that that's got to be the answer. But we have to make sure that that's what the calculus is confirming for us. Okay. That would actually give you the area. Yeah, if you went back up and you plugged it in to this formula right here that's boxed, then it would give you the area of that can, which I could have asked for that. I could have said in the problem, find the smallest area a can have and hold 1 liter. Well, you would do right here into this, you do A of 5, what was it, 5 point what? 42. So that would be 2,000 over 5.42 plus 2 pi times 5.42 squared. That's what you would do. And that would be measured in what? Centimeters squared, because it's an area. Squared centimeters. $550? Okay. Something like that. That's all I want, because I said the dimensions of the can. So I want R and H. But if I had asked for the area, you'd give me the 550 or whatever it was you got. The area with the minimum surface area, the can with the minimum surface area holding 1 liter has an area of 540 and radius, or 550. What's that? Well, how would you say it? 550 squared centimeters is the minimum surface area a can have to hold 1 liter. Yeah. Yeah. I mean, there's no like universal way of saying it. You just express it. Yeah. All right. Let's look at another one, because these are fun, as you can tell. The next example, find the point on the graph of y squared equals 4x minus 1 closest to the point 3,1. Did everyone do that problem? I'll just give everyone 100 for that quiz. How about that? That sound like fun? I'm trying to help you all out. Most of y'all seem to get it. Okay, so look, this problem, what we have is this. We have a point that's given to us. The point is the point 3,1. And then we have this parabola that opens up sideways. And we're trying to find which point on that parabola is closest to that point. So it's somewhere about there, right? And if you watch the video, I've already done this, so I'm like a scratched record here. Record? What's a record? Scratched CD? Just, I don't even know what it would be. A bad memory card? What would you say nowadays? Does anything skip anymore? Okay. So this is a good problem, because a lot of things flying through outer space travel in these like elliptical paths and stuff as they go by planets. And so you'd want to be able to say, okay, look, like where is it going to be the closest to us, right? Like, let's say this is some big old meteor or something, and the point is Earth right there. And we're like, well, if that's its path, then when is it going to be closest to us? Like, and how close is it going to be, right? This would be that sort of problem. You've seen that like on the news, right? They talk about things like that, try and freak everyone out. Barely missed the Earth. You know, like 100 million miles away or something like that. Yeah, now that's a little closer. Okay, so everyone understands the question. Which point on that parabola is closest to that one? So what is it that we're trying to... I mean, we have to get a picture, right? Got to get a picture first. Where did it go? I lost it. There we go. So you would actually probably need to know what that looked like. You wouldn't have to. Got a parabola and a point. What is the thing we're trying to optimize? The distance between the point and the function, or the curve, right? We want the minimum distance between the point and the curve. That's what we want, right? And let's just call that capital D for distance. I don't know why that D looks weird. Capital D, that's our distance. So that would be, draw me a line going to some point here. Doesn't really matter where it is. That point can be anywhere. That D represents the distance, doesn't it? I want to know where I'm going to get D to be the smallest, right? I want to minimize D. So I want to minimize D. So I'm going to need a formula for D, right? I'm going to need some equation that gives me the distance between 2 points. The distance between 2 points. Do you know the general equation for the distance between 2 points? Yeah, let's see. Let's revisit it. It's back from, I don't know, college algebra or something. If you are given 2 points in the Euclidean plane, that means on a flat sheet of paper, right? x2, y2. The shortest distance between them is a straight line. And that distance, and I'll call it little d here, is going to be the square root of x1 minus x2 squared plus y1 minus y2 squared. It doesn't matter. You could do x2 minus x1. You could do y2 minus y1. The reason it doesn't matter is because after you do that subtraction, you square it. So even if it were the other way around, the squaring would make the sign the same. Where does that come from, that formula? You just make a little right triangle, right? And then it's the hypotenuse. So you use like a squared plus b squared equals c squared. Okay, but let's get back to our picture. What is this point that's given to us, isn't it? 3, 1. So I'll call that x2, y2. What is the other point? I don't know it, do I? But it lives on that curve, doesn't it? It lives on that curve. If it lives on that curve, then there's a connection between the x and y coordinates, isn't there? How can I make the connection? Anyone know how to make this connection? If I give you an x, can you give me a y? If I give you a y, can you give me an x? So, say again? Well, look, we know that this is xy, right? I mean, it's some x coordinate, some y coordinate, right? But it has to satisfy this equation, doesn't it? So could I not take this equation, and I think I want to solve it for x because it's easier, to add 1 and then divide by 4. So that means that if somebody gives me what, I can give them what? Yes, if someone gives me y, I can give them x. So you see this x right here? I can replace that x with y squared plus 1 over 4. Y squared plus 1 over 4, and then this is still y. So I have 2 points now. I have 3, 1, and I have this. Why did I just go through that step? Can anyone tell me why I just went through that step of trying to replace the x with that? With the y squared plus 1 over 4? Like, why did I do that? What if I had just left it as x and y? What would your distance formula look like? That's right. It would still have both x and y in it, wouldn't it? You'd have 2 variables. Now you're down to 1 variable. Understand? Let's look at capital D. Capital D will be the square root of x1 minus x2. So for us, what's x1? Yep, it's y squared plus 1 over 4 minus, what's x2? 3 squared plus y minus 1 squared. Any questions on that? All right. I think I'm going to start a new page here. Well, I've got room there. So the distance between those 2 points is the square root of y squared plus 1 over 4 minus 3 squared plus y minus 1 squared. Is there a restriction on y? Because now I'm ready for domain, right? Oh, I should have put d of y in the front of this because I've got my distance in terms of a single variable. Is there a restriction on y? Is there a smallest y value and the largest y value? Look at your picture. The y-coordinate is the y-coordinate of the point along the parabola. Is there a smallest y and a biggest y? No, if I keep moving along that curve, that parabola opens up so I could keep going up forever and down forever, right? The y-coordinate of that point. So there is no technical stopping of the y. Now, I mean, we could realistically say, hey, look, you know, it's definitely not going to be negative, right? I mean, think about it. Is the closest point from that picture have a y-coordinate that's negative? Our closest point's somewhere up here, isn't it? Like right in there? It doesn't have a negative y-coordinate. But that's because we have the picture, we can say that. If we didn't have the picture, we would have to just concede the idea that y can be anything. So I'm going to put here as a domain that basically y is any real number between negative infinity and infinity. And what is the pleasure that we all have now? A derivative, right? Chain rule. Derivative of the square root of something is 1 over square root of that junk right there. All that shit that's in there I don't feel like writing. I'm being lazy, I'm sorry. On a test, please don't put junk. Put junk when you're like an engineer or something, you're out doing work for your own company or something. You can put junk wherever you want. On a test, just write it down. Okay, times what? Oh, I forgot the 2. 1 over 2 root junk times what? The derivative of everything inside. Oh boy. Should we maybe have cleaned up the inside first, or do you just want to go after it, just try and get that derivative? We'll have to do chain rule, won't we? On each of them, because they're both squared. Right? So I'm actually going to decide to clean this. I'm going to take this real quick. I'm going to rewrite that as 1/4 y squared plus 1/4 minus 3. That is what that is, right? Dividing y squared by 4 and 1 by 4 is the same as 1/4 and 1/4. What's 1/4 take away 3? Minus 11/4, right? What am I supposed to do with that? Square it, right? So coming back to this, I'm supposed to take that and square it. So take that and square it, take that and square it. So when I square that, you do like a FOIL type thing. You get 1/16 y to the 4th. Oh man, minus 22/16 y squared. You like it or no? Plus 121 over 16. I did that mentally, so anyone concur on that? It's 11/16 twice, so that should be right. What does the other one turn out to be? What is this thing squared? Y squared minus 2y plus 1, right? We FOILed that one out. Can't I add all those together now? So what is under this root? If I were to come back here and say, oh, this is just the square root of a bunch of stuff under here, what would it be? 1/16 y to the 4th. Okay. You have to put the y squareds together. 32. Reduce that fraction. Negative 27/8 if you reduce it, or it would be, right, 54/16 or something like that. Y'all realize I'm putting these two together? Oh, wait. Oh, I did the wrong one. Crapola, man. Glad y'all are paying attention. Because I'm not, apparently. So, negative 19. Nope, not negative. Positive, damn it. Negative 3/8. Negative 3/8 y squared. How many y's? Minus 2y, and then 1 plus that, so plus 137 over 16. Maybe the chain rule would have been better. I don't know. I just wanted to show you that you could do that. Because if I do that, then when I took that derivative, I would have 1 over 2 times root junk, right? Now times the derivative of what's inside. And that derivative is a lot easier, isn't it? No chain rule at all. What's the derivative of 1/16 y to the 4th? 4/16 or 1/4 y cubed minus 3/4. I'm reducing y minus 2. Yes or no? So where we are is 1/4 y cubed minus 3/4 y minus 2 over 2 times the square root of all that junk in there. That's our derivative. And it's pretty messy, isn't it? But what are the questions that we have to ask now? With the derivative, what are we supposed to ask? When is it 0? And when is it undefined? So what about it being 0? It's a fraction, right? So all you have to do is set the top to 0. I have to start a new page. All right, so I'm going to start a new page. Is that all right? 1/4 y cubed. What was it? Was it y or just y? Y or y squared? Y equals 0. All right. Ooh, I'm not happy about this. Because it's almost quadratic, right? But not quite. I don't like the fraction, so I'm going to multiply everything by 4. That's better, right? Any ideas how to solve this? We just surrender, right? We surrender. If that was quadratic, you would be in business, right? Anything you might have learned in college algebra on how to attack a problem like this without a calculator or a computer? Y'all remember synthetic division? It's called the rational zero test. You take all the factors of 8 and you write them down. Now that's only because there's a 1 in front of the y cubed that I can do this. So what are all the factors of 8? All the numbers that multiply into 8 or divide into 8 evenly. 1, 2, 4, and 8. And then you're supposed to try synthetic division on each of those. No? I know. No, doesn't factor. None of those would work. So what we've... Oh, come on. Get up here. Hold on, Mike. It's not bringing up my thing here. Oh, there it is. What we're getting here, okay, is we're trying to get this y coordinate of this point, but our algebra to find it is extremely challenging, isn't it? I mean, there's no way we're going to get it by hand, unless we made a mistake somewhere. Yes. Yes. X1 minus X2. But it doesn't matter because when you square it, it won't matter. You could do X1 minus X2, or you could do Y1 minus... Or, yeah, but even that wouldn't matter because you square it. The only difference, like if I do A minus B versus B minus A, The only difference between the two is the sign. Right? 5 minus 4, 4 minus 5. Square it, doesn't matter anymore. You just have to get your x coordinates together and your y coordinates together. That's the most important thing. So I'm sitting here, I'm looking at this honestly, everyone, and I'm like, well, that ain't too good. That didn't work out very nice. So any other ideas on how we can do this? I mean, this is where we got stuck right here, right? Back up here, didn't we, when we had xy right here, when we had that, xy, I said, well, couldn't we solve that up there for x and get it all in terms of x? I mean, sorry, and all in terms of y? Maybe it would have been better to do it all in terms of x. What would change? Let's look at what would change, okay? Can you solve that equation? I want to start a new page. If we have this equation, y squared plus 4x plus 1, right? Minus 1. And we've got this point sitting out here at 3, 1. And we're trying to describe some other point here, xy. If I solve this for y, I would get y is square root 4x minus 1, right? Then I could come back over and I could replace this point, x square root 4x minus 1. And now what would the distance be? Square root, difference of your x coordinates. X minus 3, right? Squared, plus, now difference of your y coordinates. Square root 4x minus 1 squared. That's still pretty ugly, isn't it? You could expand out x minus 3 squared. Then you could FOIL out the next one. If you did the next one, you would get this. That doesn't look much better, does it? So what I did was I took this one right here and I multiplied it times itself. So the derivative of that we could take. Let's clean it. I'm just trying to see if this is going to make it any better. It may turn out that it doesn't. So let me try and collect any like terms together. X squared, I have minus 2x plus 9 minus 2 root 4x minus 1. That's just putting our like terms together. Now a derivative, it would be 1 over 2 square root junk. But what would the derivative of the junk be this time? (2x minus 2). Then the 9 is 0, right? But then we have a square root we have to take derivative of. So minus 2 times 1 over 2 square root 4x minus 1 times 4. How does this look to you? I would cancel those 2's. What is the numerator? Put all that numerator on top of that junk. What would you have? 2x minus 2 minus 4 over square root 4x, good, minus 1, but then all of that over 2 root junk. Can you set that equal to 0? Yes? So just set the top to 0, right? I'm going quickly through this, all right? I'm not doing this formally. Set the top to 0 and try and solve that. How about getting a 2, dividing everything by 2? Just to get, each term has a 2 in it, right? So let's just get rid of the 2. What next? Yeah, there's several different approaches you could take here. I'm going to move the term with the square root in the bottom over to the right side of the equation. And now I'm going to multiply both sides by the square root. So I have square root 4x minus 1 times x minus 1 equals 2. And now I'm going to square both sides. When I square the square root, it becomes 4x minus 1. When I square x minus 1, I get that. And when I square the other side, I get 4. Now I'm going to expand x minus 1 squared to become x minus 2x plus 1 equals 4. And then multiply out. So what I mean by that is expand this, 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 this. So 4x squared. No, yeah, right? 4x squared. Oh, wait. Sorry, I messed up. Sorry, that's a square. I knew something was wrong there. There's a squared there. Everyone catch that? I missed that squared right there. So that first one should be 4x cubed minus 8x squared plus 4x minus x squared plus 2x minus 1 equals 4. Collect like terms, 4x cubed minus 9x squared. So where am I? 4x cubed plus 6x plus 5 equals 0. I'm trying to get into, minus 5. Yes, thank you. All that work, and where did we get? It looks cleaner, but can you solve it? How are you going to find that? I mean, that's what we have to set equal to 0, right? That's what we have to set equal to 0. That's called, you can't do that. That's one of the things about the zero factor property. Whenever we say something like x times x plus 5 equals 0, you set each of these equal to 0, don't you? I mean, then in that case, why don't you just put the whole left side into your calculator and get the x-intercepts? Yeah, yeah. So what I guess the moral of the story is here is that either way you do it, you end up with a cubic equation that we can't solve with any algebraic method, right? So we have to have some way of finding zeros, right? Like, how can we Find zeros. Well, what do we know can do it for us? The calculator, right? The calculator. So I'm going to use the calculator, but this is leading us, the reason for this problem is because the next section deals with Newton's method, which is an introduction into how a computer solves this. Okay? Just so we can understand the importance of it. Here it's just, we want to try and solve this problem. We get stuck at the end, so the technology will help us finish it off. So I'm going to come into I have a TI-89, but you could go to Wolfram Alpha and just put solve and type that in. I'm going to do solve 4x cubed minus 9x squared plus 6x minus 5 equals 0. I get through my calculator x equals 1.802557749 Now, you don't have to put all those decimals, but again, I'm trying to lead you into the next section, all right? That's what my calculator says. Anyone else get that? That knows how to use that, any of those features on their calculator? If you want to learn how to use your solve function, if you have a TI, it can do this. Now, what would we still need to do here? 1.802. What would we still need to do? Assuming we got that. Number line. 1.802. Then we would have to do test points. Plug those into the derivative. And what we would get is this. I'm going past that because of time, all right? We could verify it's a local minimum. Now, on a test, I would never give you a problem where you'd have to use a calculator. It would turn out to be a nice thing that you can solve. But don't be surprised if you were to see a problem like this where it says find the minimum distance between a point and a curve. It's just that, what's that? No, that's the x-coordinate of the point. That's the x-coordinate of the point. So what we would still need is the y-coordinate. So plug it into the equation that we have for y. What was y? It was the square root of 4x minus 1, wasn't it? So if you go y equals square root, well, I won't even, just plug in 1.82. Oh, whoa. I used the solve feature on my calculator to get 1.082. I'd be happy to show you that when we take a break. So according to this, it looks like 1.082, 1.824 looks like the point. We got, for the x-coordinate, it was it 1. Oh, it was 1.802. Oops. 1.802. Let me double check that. I think I did the other calculation wrong then. Yeah, I did. 4 times 1.802 minus 1 square root of that. 2.49? 2. We're about to find out if this is right. How am I going to find out it's right? There's a couple of ways I can do it. Why don't I go out to this picture right here, and why don't I snap to the solution? And what's the solution? 1.8, 2.5. And the actual distance is 1.9. How do I get the distance? Go back to that capital D equation before you took the derivative and plug in your x and y into it. Any computer science people here? I think I've asked that before, right? Are there any in here? No? Yes? Okay, so look. You know how it said snap to solution there? And it just popped to the answer? In my code here, this is the code that I wrote to make this thing happen. I should have somewhere in here yeah, but somewhere in my code I should be taking a derivative. Maybe I didn't. Okay. All right. I guess I went and computed the answer on paper somewhere else or had the computer do it, but all right, we're going to take a break. I think y'all are ready for it, right? Let's say 10 minutes, right? Let's come back around 3. All right, I'd like to maybe do one more problem in this section, optimization. Because like kind of we had with the related rates, none of the problems are exactly the same. They all have different sorts of things involved. So I'd like to get something kind of different from what we've done already. Here's a classic, how about a very classic problem, one that a lot of Cal 1 classes will cover. Find the dimensions, dementia? Is that what you said? Find the dimensions of the cone with maximum volume, which can be inscribed into a sphere of radius 1 foot. Okay, so your cone is, well, it's a sphere. It's a cone inside of a sphere. It's a cone inside of a sphere. So find the dimensions of the cone with the maximum volume that can be inscribed into a sphere of radius 1. So here's a sphere, right? 3-dimensional sphere. Ooh, that's a pretty good sphere. And I want to put a cone inside of it, and it needs to be inscribed. Now, what we mean by inscribed is that it's going to touch the edges of the sphere. So imagine a cone whose base, the tip touches, let's say, the North Pole, and the base touches somewhere on the cone. The base of the cone touches somewhere on the sphere. Like I could do this instead, right? I could make a cone that goes to the equator of the sphere. Do y'all see that cone? That would include around here. Is that going to give me the most area? Not area, volume, sorry. Maybe. Maybe that's the most. See, what do I gain? By doing the equator, I'm the widest I'll ever be, right? But I'm also the shortest I'm ever going to be. If I come down on that from the equator, if I come down a little bit, I'll touch around here, and then I'll be something like that. So now I've given up width, but I've gained height, haven't I? So what are the dimensions of the cone that would give me the greatest volume? Does everyone understand the concept of the problem? These are classic problems. Another one is a right cylinder inside of a sphere. So a beer can inside of a sphere. That sort of thing. Or a beer can inside of a cone. So there's all these different variations of this type of problem. And I can remember as a Cal 1 student, the first time I saw it, I was like, what the? You know, I was just like, what the heck, man? The algebra in it, or the geometry in it's just all weird. Yes?
I don't understand the point of the sphere. If you're just trying to find the sphere is your constraint. Well, yeah, the sphere, the 1 foot radius would be constrained.
Yeah.
So you don't really need to visualize the sphere.
But the sphere is fixed, right? It's just sitting there. And there's an infinite number of cones you can put inside that sphere that would touch the North Pole and touch along the edge of the sphere. You can imagine moving down, it would get wider, and then it would get more narrow, right, but taller. So each one of those cones has a different volume. Which cone has the greatest volume? Maybe. That's a good conjecture, but there's only one way to show it, and that's by finding an objective function, finding your constraint, and then optimizing it. So what is, let's go through this process. What do we want to optimize? Optimize what? Optimize the volume of what? Of cone. Now, if I'm going to optimize the volume of the cone, I may as well start talking about some dimensions here on this cone. I'm going to get rid of the blue cone. You might need to redraw the whole thing. I'm going to work with this red one. Maybe I'm not. Oh, shit. I erased my whole damn cone. Yeah, I'm just going to start my whole damn thing over. Never what? I didn't hear that. What? Never put what? Yeah. That's all crooked too. Oh, well, who cares? Okay, we've got a cone inside of an egg. So that cone has a height to it, doesn't it? The cone has a height. I'll call it H. And that cone has a radius to it, which I'll call R. And do you agree that depending on how I design the cone, the height will be different and the radius will be different, right? None of those are fixed as I change the shape of the cone in there. All right. What is the volume of a cone? Because that's what we're trying to optimize. What is the volume of a cone? Volume of a cone is 1/3 pi r squared h. That's what we want to optimize. Right now, the volume depends on how many variables? 2, r and h. What do I need to get it down to? Just 1. So I need somehow to come in here with a constraint. What is my constraint? I have to live in the sphere, right? And the sphere is fixed. But how is that going to get me the constraint? Yeah, I mean, this is a tough one to see right away. The height could be twice the radius of the sphere. So the biggest the height could be would be 2, right? Because the radius of the sphere is 1. Yeah, I agree with that. Anything else? So the radius could be as big as 1. Agreed? But what we need, look, what we need here is what we've needed in every other problem we've done. We need an equation with R and H in it, don't we? Other than the volume equation, because we already have the volume equation. Anybody see this? No? By nobody answering me saying they see it, I take it as this one. It's not obvious here, right? The equation.
I don't know, but I think you don't have to get the volume of the sphere, and that kind of equation that you use the volume, and that's either volume for R, or volume for H, or something. I don't know.
Okay, that's so you're thinking I can figure out what the volume of the sphere is, and plugging that in for volume right there for V. The problem with that is the volume V, right? That volume V is the volume of the cone. And so there's no way that cone can ever have the volume of the sphere, right? Because it's inside of it. It's a good, I mean, you got to try something here, right? Okay, how about bonus points for anyone who can come up with an equation relating R and H together right now? Well, I just want to make sure, like, everyone in here convincingly does not know how to proceed with this. The volume has R. Yes, okay, good point, but it's not going to help us. This is the objective function, okay? This is the objective. We can't use the objective as our constraint. The constraint has to be some other relationship between R and H. Okay, so we'll proceed. No, we'll proceed. Bum, bum, bum. All right, let me help you out, okay? Let me help you out. We'll see. We'll see. What is this? Just look at it for a second. What is it? It's a what? It's a circle and a triangle, right? Now don't get, I didn't mean to make it look equilateral or anything. There, is that better? Okay, so this is a circle with a triangle inside of it, isn't it? Now let's go back up and look at our picture. That was a cone with a sphere, right? Imagine taking a knife and cutting the sphere right down the North Pole, just right down the center, right? A cross section of that sphere cone thing we're making, right? You would then create this shape right here, correct? A and B. I need any relationship I can find between R and H. From where? Oh, no, but we can't use this. Wait. Yeah, we can't use the constraint. I'm sorry, we can't use the objective. We can't use the objective because, look, what we're trying to do is, in the objective, we're trying to find a replacement for R or a replacement for H. So if you use an equation to replace itself, at the end, what you'll get is something like V equals V, and that's all it's going to say. Look, let me take you the rest of the way, okay? Let me take you the rest of the way. Here's the center of the circle, right? Now, we know that the distance all the way from the center to the bottom of the triangle to the top of the triangle, right there, that green dotted stuff, which now I'll make it green solid, that is h, right? Agreed? We don't know what that is. Now, we also know that the distance from there to there is what? R, the radius. We do have a triangle. It's a right triangle. But that hypotenuse doesn't lend itself very easily to revealing what it is, does it? Because all you could say is it's the square root of r squared plus h squared. However, there's something that we haven't addressed, and that is the fact that the distance from the center to here is what? That's 1. And the distance from here to here is what? 1 also. Agreed? And what is the distance from here to here? That's 1. Agreed? What is the distance from here to here? How long is it from the top of the North Pole down to the bottom of the triangle? No, not from the top to the South Pole. From the top to the bottom of the triangle. No. From here to here is what? That's h. The yellow is h, right? This, the blue, the little blue, the highlighted blue right there, isn't that 2 minus h? Isn't it? I'm just like labeling every freaking thing I can here. I'm trying to come up with a relationship here. Huh? Well, I mean, I know where we're going. Yeah. But I'm trying to, like, when you're looking at these problems, you try and start to extrapolate as much information as you can from the picture. I see a triangle I really want to go after. It's right here. You see this right triangle right here? It has R in it. It has a hypotenuse. If I could just get that other side in terms of h, wouldn't I have a relationship? Right? So let me draw that, get that h out of here. That green triangle, that highlighted green one looks like this. This was R. This was 1. Yeah, it's this. It's this part right here, which is 1, right? That's 1 right there, all the way to the bottom. Take away how much? 2 minus h. So what is 1 take away 2 minus h? Negative 1 plus h? H minus 1? I mean, there's so many freaking ways you could see that. I think that way that I just showed you is way too complicated now that I look at it again. Right? So, peace out. Let me try a different approach. Just a quick one. Here's our half triangle. It looks like this. There was the piece we were looking at in there, right? We knew this side was H. We know this side is R. And then I came out from the center of the circle out to here, called that 1. So the distance highlighted yellow, how long is all of that right there? H. So if you want just the distance from here to here, it's H take away this much, which was 1. So H minus 1. Much easier. But see, that's the thing. On these problems, there's no like, okay, every time I see this, I will look at this relationship. No, you have to look at all the different geometry possible things that could happen and come up with your relationship. So here, this side now is what? H minus 1. Now do we have a relationship between r and h? Yes. R squared plus h minus 1 squared equals 1. Which means I can put r squared equals 1 minus h minus 1 squared. Do I need to solve it for r? Like, do I need to take the square root on both sides here? No, why not? Yeah, look back at your volume function. What's in the volume function? R squared. Beautiful. I have r squared, don't I? In terms of h. I don't know if beautiful is the word we would want to use, but try and get this in here. So going back to our objective function, it was volume equals 1/3 pi r squared h. We are now going to replace the r squared with our constraint, which is 1 minus h minus 1 squared, and then times h. Let's FOIL that out inside, expand it. 1 minus h squared plus 2h minus 1 times h. Just make sure I did that right. H squared minus 2h plus 1. Wait, hold on. What? Did I? Minus 2h plus 1. I'm not sure. What do you? Yes? Minus 2h plus 1. But I already distributed the negative through. You see? Do you see what I'm saying? Like, I took this right here, and I figured out that was h squared minus 2h plus 1, right? But then there's a minus in front of that that would distribute to each one, which would make it the next line. And then the ones cancel, and then I distributed that h that's sitting at the end through. And I don't know if there's something just about me. I don't like the negative in front of the h cubed. So can I put negative 1/3 pi times h cubed minus 2h squared? That's my volume. In terms of a single variable, right? Questions? Can I move to a new page? So we're here. The volume is now in terms of a single variable h, right? It's negative 1/3 pi times h cubed minus 2h squared. Please check. My brain has stopped working. Is that what I just had on the board a second ago? Okay, now what should we think about? Good, good. Is this a closed or an open interval? So our variable here is h, right? Is there a restriction on h? Absolutely. What's the smallest h could be? You could have a cone that went all the way up to the North Pole and just became a point, right? You'd never do it, but you could have it. 0 would be the smallest. What about the biggest? 2. Because that would make a cone that would get, you know, wider, and then at the very bottom it comes all the way. So it'd just be like a line connecting the North and South Pole together. It had no volume to it. But we definitely have a restriction here, which is good. What? Uh-oh. That can never be good. Oh, I know what happened. Oh! 0. There we go. That's good because it's a closed interval method, right? Is that a continuous function? Yeah, it's polynomial. So let's fire the derivative out real quick. Negative 1/3 pi is a constant. So I just stick it out there. Derivative of this is 3h squared minus 4h. I want to set that to 0 now, don't I? So the derivative will be equal to 0. Means I have to set negative 1/3 pi times 3h squared minus 4h equal to 0. I can just kill off the negative 1/3 pi because it's just a number being multiplied. I can factor out an h. And what are my answers? H equals 0 and h equals 4/3. How did what? The 0 and 2? Okay, go back to the picture, right? The height was the distance from the North Pole down, right? That was our height. So think about a cone that the height would be 0. That means bring the bottom of that cone all the way up to the North Pole, and basically we get, you know, smaller and more narrow, and it would go to a point, and it would be basically not a cone anymore. But that would be the smallest height you could have. And then the biggest it could be would be 2, because remember the radius of the sphere was 1. So that means the diameter of it is 2. So to go from North Pole all the way to the South Pole would be 2. That better? All right. Anything else? I need to know if this is ever undefined. Is it? Is the derivative ever undefined or not exist? No? It's a polynomial, so we're good. So what are we going to do now? Because the closed interval method's different, right? What do we do? Plug these points into, and the endpoints, into what? The original function, not the derivative. So I want v of endpoints, and I want v of the critical number 4/3. So what's v of 0? Go to your volume function, plug in 0 for h. You should get 0. Okay, plug in 2 for h into the volume function. That's up here. Plug in 2. You should get 0 again. Plug in 4/3. And you might need a calculator. So 4/3 cubed. I'm doing it times pi. Oh, I'm doing all that on my calculator here. I'm getting 1.24. Anyone else getting 1.24? Yes, no? Maybe so? Yes, no? Maybe so? No? No one agrees.
I don't know.
1.23? At 1.24. Did you use pi key or did you use 3.14? You got 1.2411? Something like that? Anyone else get 1.24? Look, it's 1 point something, okay? The point is, with this method, we can convince ourselves that's the max, right? That's the max. But I didn't ask for the maximum volume, did I? I said, what are the dimensions? So the height of this, I'm getting to the point of my answer here. The height of this cone needs to be 4/3. What do I still need to determine then? The radius. So where did we have a formula for the radius? Way back where? It was this one. It was radius squared equals 1 minus h minus, was it h minus 1 squared, right? So I could say then that the radius is the square root of that, but plug in 4/3. So I'm going to do that. I'm going to do 4/3 minus 1. I'm going to square that. Square root of 8/9. .94. Okay. 0.943, something like that. And h of course is like 1.33. And they didn't ask for it, but the volume would be 1.24. And this would be in feet, height and radius would be in feet, and then this would be cubic feet. So the biggest volume you're ever going to get is 1.24 cubic feet. It'll happen if you let the height be 4/3 of a foot and you let the radius be 0.943 feet. Things like this are used, believe it or not, are used in things like packing. Like companies when they, determine the best way to pack things so that, they want to ship a bunch of their product out, but their product has a certain shape to it. So how do you pack it so you can get the most in a box, and what's the most efficient way? You're trying to maximize the space in the box, right? Things like that. I mean, it's much more complicated usually, but this is the basic concept behind it. All right, that's going to end it for optimization, which brings us to Newton's method. This will be the last thing we talk about today. Then we'll come in and we'll do antiderivatives on Monday, and we'll talk about the test. And 5.1, I want to talk a little bit about chapter 5. Just a little bit. I know this is a long day, huh? Long day. 4.6, Newton's method. How many of you watched the video for Newton's method? Okay. It's actually really interesting. Do you remember at the beginning of this class, somewhere at some point in time, we were talking about the intermediate value theorem. I was telling you how a calculator solves an equation where it takes, like, let's say you have an x-intercept here, so your calculator would take a test point on each side and it would test to see if it was positive and negative and look for the change in sign and keep going back and forth. That's called the bisection method. The drawback to the bisection method is that it has a very high operation count. It takes a lot of operation count, or a lot of computations by the computer to get to your solution. Newton's method converges faster to the solution. So you might only need Newton's method 3 times, where bisection might take you 1,000 operations to get to the same tolerance. So it's just a way of approximating or getting solutions to equations. For those of you who didn't watch the video, here's basically what it says. No. It says that if I'm trying to figure out where a graph crosses the x-axis, I can pick some random point on the function, and I could take the tangent line like this. Oop, that's not very good tangent. And it'll cross through somewhere else. You know what? I have the best picture. It's the one I did on my video. Here it is. So if I'm trying to find where this thing touches the x-axis, I pick a point out here, just randomly pick a point, go up to the function, find the tangent line. That tangent line will come down. Wherever it hits the x-axis, I go back up and I pick that point. Okay? Then take its tangent line wherever it hits the x-axis, go up again, and then do the same thing. And if I zoom in, you can see that every time I do this, I pick another tangent line. Wherever it goes up and hits, now I zoom in really, really tight, that it keeps on getting closer and closer to that 0, doesn't it? So it gets there extremely fast. It only took us like, what, 4 or 5 operations there, and we were done. So what it creates, though, is a sequence of points. The first point we had was the one that we started with, right? We guessed it. And then that, doing the tangent line, gave us a second point, then a third point, then a fourth point, then a fifth point, right? And those points, we are going to call them x1, x2, x3, x4, x5, x6. And what we have is that this sequence of points converges to the x-intercept. And Newton's formula, or the formula for Newton's method, says this. It says x sub n plus 1 equals x sub n minus f of x sub n over f prime x sub n for n greater than 0, greater than or equal to 0. This is what we call a recursive formula. What happens is you give me the initial point, and this will generate the next point. Then use that point to generate the next point, then that point to generate the next point, and then that point to generate the next one. So let's just do an example, and hopefully you'll start to see how this works. Let's find the solution to the equation x squared minus 2 equals 0. Now we know the answer to this, right? What's the answer to this? No. What's the answer to the problem? Like if we were in college algebra class, I said solve x squared, square root of 2, negative square root of 2, right? Well, that's how we would do it algebraically. Take square root, plus or minus. And then on a calculator, you get plus or minus 1.414, something like that, right? Blah, 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 blah. Yes? Okay. But what if it's an equation we can't solve, but like this? Well, have we ever run across an equation that we can't solve in this class? Like a little while ago, right? Okay. So we could do it on the calculator, as some of you did. Y'all came up here and I showed you how to do it. Now, how is your calculator doing it? It's doing this. Okay, so behind the scenes, your calculator is finding this sequence right here and watching it converge to an answer. And we'll see it when we work it out right now. We'll see it start to converge to 1.414. So the first thing we have to do, folks, is we have to guess what the answer is. So let's just guess. Well, we're going to do 3 because it'll match the picture that I did here, because I did 3 to start, and everything will match up after that. So I want to stay with that. So I'm going to let x0, that's going to be my first point. I'm going to let x0 be equal to 3, and that's my guess. Now, according to the formula up here, if I replace the right side of the equation here with x0 minus f of x0 over f prime x0, that should be equal to x sub what? 1. So if this n is 0, this over here is n plus 1 would be 1. So the next x value, the x sub 1, should be whatever that computes to be. If I replace this n here with 0, that with 0, that with 0, then this side becomes 0 plus 1 would be 1. So now I have the 1 here, I've got 0, 0, and 0. Now, what is f in this problem? What's the function? It's the left side of this equation. It's f. This is our f of x. While we've got it here, if f of x, if f of x is x squared minus 2, then what's f prime of x? What's its derivative? 2x, right? Now we need that because I'm about to come back over here and compute x sub 1. It will be x sub 0. What was x sub 0, everyone? 3 minus f of 3. What's f of 3? Plug 3 into the function. 7, right? 9 minus 2. So 7 over, plug 3 into the derivative, you get 6. What's 3 minus 7 sixths? You have to get a common denominator there. (11 over 6). And what is that as a decimal? Just to get an approximation. 1.83. Now, I'm not going to use that, but the reason why I wanted you to see that is because I want to come back up to my picture. I wanted you to see that the next point that I get, I started with 3. This next point right here looks like it's about 5, 6, 7, 8, 1.83. So that point is coming from that computation. Now what we do is we use that to get our next point. Understand how this is flowing? So what should my next one say here? X sub 2 equals 11 sixths. We are not going to use the decimal, okay? We're going to use the fraction. 11 sixths minus, how about f of 11 sixths? We'll compute it in a second. F of 11 sixths over f prime of 11 sixths. There's not a whole, this isn't a problem like, cut the sphere in half and notice these triangles and all that. This is very mechanical. These problems is just plug and chug. You just got to know how to apply the formula. So this is 11 sixths minus, 121 over 36 minus 2. I'm getting 49 over 36 over 22 over 6. And then you can flip and do all that stuff. I get something like this. 11 over 6 minus 49 over 132. Which is 193.13 or over 132. Positive. Which is approximately, man, why does it keep doing that? This is approximately 1.462. Any question where any of those numbers came from? I mean, I skipped some steps. I just had my calculator do it, but you could simplify those fractions, hopefully. And then, if you look back at this here, my second point was right in here, right? So I'm going to zoom in on it. It should be really close to 1.4. What was it? 1.4 something? It's right in here. So let me really go in here. Yeah, here's 1.41. So here's 1.45. Here's 1.46. What do we say? 46 what? 2. So yeah, it's pretty close, right? And now we do that again, and we come over here. And look how close we are on the third application of Newton's method. On the third application, look how close we're going to be to the true answer. Right? And then you could keep going. I'm not going to... Did I have it compute? I think I did. Fourth. Yeah, there's the value. At the 4 time, we're not going to do anymore, okay? We're going to stop here. But if we did it again, this next one would be 1.41498, which is really close to what square root of 2 is on your calculator, right? If we go again, 5th iteration, we're 1.414213. See, we're ready for most books. 1.414 would be sufficient. Now, depending on if you're building let's say a deck, a wooden deck in someone's backyard, your tolerances don't need to be within 1,000th of an inch. If you're building an aircraft, then we're talking about tolerances that are really, you would have to go further than this, perhaps. But that's okay. Just reiterate one more time. Understand? But it gets there. The whole point of Newton's method is it gets there fast. There's even better methods than Newton's method out there also. Yeah, we're good. I think, did I assign the homework problem out of that? 4.6? Who has their book? I don't have mine with me. Thank you. Okay, I'm going to say for 4.6, why don't you try number 7? And number 13. 13 is a good one because on 13, here's the equation. There's the equation. Four or five. Did I not give 4 or 5? I think I did last time. I'll put it back up there. Here you go, Elias. See, because number 13, that's the equation. And that's pretty similar to what we got stuck on, isn't it? So yes, we know the calculator can do it, but now we're showing with Newton's method how it's done. I would, if we were all fresh and feeling good today, I would show you where Newton's method came from. It's in the book. I doubt you all feel the attention span right now to have me show it to you, so I'm not going to. But make sure that you work these out, okay? Because I will ask you a Newton's method problem on the final, because I think these are easy points. I mean, this should be easy points on a problem like this. Hopefully. It's just plug and chug. Last class, we had the homework assignment. Let me see if I can find it. Okay, there's the homework from 4-5. So for next class, you have no videos to watch, all right? All you have to do is get caught up on your homework. So focus on all those, the graphing, the sketching, the graphs, if you haven't done those. 4.5, those are all word problems, optimization. 4.6 is going to be the Newton's method, 2 problems. Come in on Monday. We'll finish up 4.7, and we'll talk final. And maybe a little 5.1, we'll see. Quiz from last time. Yep, I'll take that. Just set it here. And everybody that's here gets 100 today also. I'm just going to note that. I'm just going to count 100, then on top of that. That's all right, just like that. Everyone have a good day. I'm going to let you go.